Okay, so
Jag kanske borde börja skriva nu och sen satt jag liksom...
So okay, if you remember, we talked about this formula that e to the power of I theta, if theta is a real number, is equal to cosine of theta plus I sine theta, even though I didn't really rigorously prove this one for you, but I actually motivated you why this formula might be correct, yes? Then I wanted to extend this formula so that it is not only correct for real numbers, it should also, my demand is that I want to make it somehow that this formula is also correct if theta is a complex number. If I want to do this, I prefer to do it in this way, so that I want to write cosine z plus I sine z, yes? Okay, then of course I told you that I was a little bit confused myself first, but when I thought it is not possible to prove this, because when I want to prove this, it means that I need to know what is the left-hand side, I need to know what is the right-hand side, and I need to show that what is in the left is equal to what's on the right. But this is not as simple as that, because you might ask me what is the sign of a complex number, yes? Okay, so we don't have any definition for sine and cosine when z is a complex number. So using this as an excuse, as a way of thinking, I want to define cosine z and sine z in a way so that this formula holds when z is a complex number. And then we came up with this answer, if you remember. If you have forgotten, you can go and watch the video. But we come up with this definition, even though it is weird, but it is good because, let me write the definition here for you. It was this formula, 2 times I, and then cosine z, I defined it as e to power I z plus e to power minus I z divided by 2. So these two were the definitions of sine and cosine when z is a complex number. So sine and cosine for complex numbers has nothing to do with the unit circle. So that is just something that we define it in this way. Okay? Okay, so now let me just solve one example here. So one strange thing is here. For example, I can ask you solve this equation, sine z is equal to 2. Of course, if I ask you sine x equals to 2, solve it, you immediately say that there are no solutions because sine cannot be greater than 1. But here I'm asking you to solve sine z equals to 2. But this is actually possible here. You will see why. So what do you think? What is your suggestion? I want to solve this equation. So let me write an example. So what do you think I should do? I want to find all complex numbers so that the sign of those complex numbers all are equal to 2. So what should I do? Exactly, thank you. There is nothing to do, yes? Sine z has a definition, so I have to use it. So sine z is e to power iz and minus e to power minus iz divided by 2I equals to 2. Okay? So, but I need to solve this one, so you can forget about this and try to find z from this equation. So I don't know, what is your suggestion? For example, I can multiply both sides by 2I, so it becomes this. It becomes 4I. Yes? Okay, then how should I continue? No, ln of both sides, first of all, it is not possible, it is not easy because we don't know what is the logarithm function in complex numbers. That is a little bit complicated. But even if we could do that, ln will not help because if I, let us consider the real numbers. If I have this combination, if you take an ln, you cannot go further, yes? Because there is no rule for the ln of the difference of two numbers, yes? If it was a product, yes, might be it was good, because ln of, I don't know, x times y, I can write something, ln of x plus ln of y, but ln doesn't work here. Yes, do you understand, Sander?
Yes.
Yes, so this is why ln is not a good idea. Okay, another guess.
Rewrite them as x plus iy, or the subset x plus iy.
Yeah, might be it will work. I don't know exactly right now, but I think it should work. Yes, but before doing that, can I do something better? Before that stage. So what is the relation between these two? If I ask you what is ex and e minus x, what is the relation between these two numbers? If one of them is 2, the other one is 1 over 2.
Yeah.
Because e to the power of x, e to the power minus x, they are reciprocal of each other, yes? So that's the idea. So I would say that let us use the auxiliary variable method. So these are experience. So you need to see some of these problems to have some experience for future. So I would say let e to power iz be, for example, call it capital T. Yes? Let me call it T. And then e to power minus iz becomes 1 over t. Agree? But what type of number t is? In general, t is a complex number. It's not a real number. But now let me put this back here. Then it becomes t minus 1 over t is equal to 4i. And then this, I multiply both sides by t, so it becomes t squared minus 1 is equal to 4it. And then I move it to the left, it becomes t squared minus 4it plus 1 equals to 0. Yes? And this is a quadratic equation, so I can solve this quadratic equation and find t. Okay, so what happens? Do you remember the formula? It's minus b, which is 4i, plus or minus. This number to power 2 is 16i squared, but I squared is minus 1, so it becomes minus 16. And then minus 4 times a times c, which is minus 4, divided by 2. Yes, this is t. Yes?
It's minus 1.
Ah, thank you very much. Thank you. This is minus 1. It was right on time. Because this becomes positive now. Yes, thank you. So then what happens? This becomes minus 12. So it becomes 4i plus or minus the square root of minus 12 divided by 2. But the square root of minus 12, I can write it as a square root of 12 times minus 1. So it becomes a square root of 12i. Yes, but square root of 12 can be written as 2 square root of 3i. Yes? So then I put it here. So this becomes 4i plus or minus 2 square root of 3i divided by 2. But I divide by 2 now, so it becomes 2i. I divide this by 2 as well. But I can factor an I out, so it becomes 2 plus or minus a square root of 3i. So I think it is a good progress, yes, because I was trying to solve this equation. It was a little bit hard, so I introduced an auxiliary variable. Then I was able to find that auxiliary variable. Then I bring it back to this equation now and try to solve this simpler equation. Yes? So what I can do now, so what can I do here? I would say I have two scenarios, yes? So I have two numbers for t. One of them is 2 plus the square root of 3i. One of them is 2 minus the square root of 3i, yes? And then what I do, I will go back here. So if t is equal to 2, so let me write option 1, option 2, yes? So this is number 1, this is number 2. So let us consider number 1. E to the power of iz is equal to t, but t is here in this case. And now I will use what you said. Yes? Even though, be careful about this point. Be careful about this point because what Sandler actually told me essentially works here. So you might think that I can take ln, that is true. I can take ln of this. Ln of this expression becomes iz, but this becomes ln of this expression. But be careful. This is not defined for you yet. So you know that even though, so we want to define them in the future. If you study a little bit more advanced complex numbers, you will see that how they define a logarithm of a complex number. But at this level, you are not allowed to use it because if someone asks you what is the meaning of ln of this, then it would be a little bit problematic. Okay? So it is correct, but it is not at the level of your lesson. But so we need to change the way that we want to think about. So this is why I will choose yours, yes? Even though that's also correct. But when I want to choose yours, I would say that let z be equals to x plus yi. Okay? I'm looking for z. Z is my question mark. But now this question mark is on x and on y. And I put this back into this equation, so it becomes I. Instead of z, I put x plus yi, and then this becomes equal to 2 plus square root of 3i. Okay? And then what happens? This I want you to see how you solve the problem. So ix, I multiply I, it becomes ix, I multiply I, it becomes minus y, is equal to 2 plus square root of 3 times I. I need to find x and y without the notion of ln. I can use ln if I am dealing with real numbers. If in somehow you need real numbers, that's okay to take ln from. But this is not still in that form. So what is your suggestion how to continue? By the way, you do remember this is defined because we already defined what do I mean by e to power z. Do you remember? And we explored some properties of this complex function. Do you remember what was that? I told you that you need to write it as e to power x multiplied by cosine y times I sine y. Yes? What is x? X is the real part of this number on top. Y is the imaginary part of this number on top. So if that is true, and then do you remember I asked you this question, what is the absolute value of e to power z? What is that, do you remember? It's e to power x, yes? So now, if I want to do the same thing, what can I do? I can say that if this number is supposed to be equal to this number, then the absolute value of this number should be equal to the absolute value of that number, yes? This is clear. But if I ask you what is the absolute value of this number, can you tell me what's the absolute value of this number?
90 degrees.
No, that's his argument you're talking about. Absolute value. No. No. So this is the imaginary part only.
Oh, yeah, so it's just that.
This just that, yes. That's exactly this number because so what you said, you were thinking that this is the real part, this is the imaginary part. No, the whole expression is sitting next to I, so this is the imaginary part. Yes? So the real part is 0. So 0 to power 2, this number to power 2, yes? And this number to power 2 becomes what? Becomes the same number. So the absolute value of this number is nothing except this. Yes? But what is the absolute value of this? According to what you told here right now, what you need is on the board.
Minus y.
Not minus 1.
Minus y, she
Minus
said.
y.
E to power minus y. Because if I ask you what is the absolute value of exponential function, you just answered e to power x. But if I ask you what x is, you would say x is the real part of this number. But what is the real part of this number is minus y. So this becomes e to power minus y. But now, can I use ln for solving this? The answer is yes, because y is a real number now. So I can use ln because I am working with real numbers now. So minus y becomes ln of this number. But I am looking for y, so y becomes minus ln of that number. This is not ambiguous for us. If you ask me what is ln of 2 plus square root of 3, this I probably know. But if you ask me what is ln of 2 plus square root of 3 times I, that's a complex number. I still don't know. If I want to use it, I have to define it for you first. So this is y, but how can I find x? That is also easy, yes? Because what I can do, e to the power of minus y is this number. But this number can be written as e to power ix multiplied by e to power minus y. But e to power minus y is this number. So instead of this expression, I put 2 plus square root of 3 times I.
So it's just...
Yes. And then I can simplify this with that. Then e to power ix becomes I. Yes? So now I need to solve that one. So it is not that easy, you know. You need to do a lot of things. So this means that e to power ix is equal to I. Do you agree with me here? So what I did, I decomposed this into this product. E to the power of minus y is this expression. I replace that one with this number. Then I simplify these two. E to the power of ix is left on the left, and then this is left on the right. Yes? And then I need to solve that one. But how should I solve that one now? I need to find x. X is a real number. That is essential assumption here. So what can I write? There's one. Yes? Exactly, because I told you that if theta is a real number, e to power I theta is the famous formula. It's cosine theta plus I sine theta, yes? This we learned. So this x is real number. So what I can do, I can write this as cosine of x plus I sine x equals to I. But the left-hand side is a complex number, the right-hand side is a complex number, they are supposed to be equal. This cannot happen unless the real part matches the real part, which is 0, the imaginary part matches the imaginary part, which is 1. And now I'm asking you, what is x? Cosine is supposed to be 0, sine is supposed to be 1. What that x is? Pi over 2 plus 2n pi. Yes, any multiple of that is possible. So what can I conclude here? X is pi over 2, as you said, but plus 2n pi. Because I need to find all of them when I ask you to solve an equation. Now, everything is now clear. You see, you have infinitely many solutions. Sine z equals to 2. In real numbers, you didn't have even one single solution. But in complex numbers, you have suddenly infinitely many solutions. So what you need to provide as an answer you need to provide that z is equal to x, which is pi over 2 plus 2n pi, plus y. What is y? This is y multiplied by I. So this would be minus ln of, 2 plus the square root of 3 times I. Yes? So this is one answer to that equation. So you have infinitely many answers for one of them. But of course there is a second option. I can leave that one to you. That would be a little bit technical. Okay, but not technical. That's exactly the same story, but you will see how it goes. So you should consider this one as well, and then you find another type of solutions. So you can continue that one yourself. So is that understandable? Yes? There are some problems. Let me solve some of them for you. So for example, let me solve an example just from real numbers. If you remember, if you go to Math 5 book, when we were dealing with mathematical induction, I think we had this or similar. I don't remember exactly, but I remember, I think I solved this problem for you. But of course, I want you, so theta is a real number, whatever you like. 1 plus cosine theta plus cosine 2 theta plus up to continue cosine n theta. But in mathematical induction, I have to give you the right-hand side, and I ask you to prove it. So then always this becomes evidence. So how people found the formula. Because if the formula, I give the whole formula for you, then you can use mathematical induction on n to prove that that result is correct. But if I don't give you anything on the right hand side, is there any way that we can find a closed formula for this sum? A closed formula means something which is equal to this that does not include these dot dots. Yes, that's a closed formula. So you see, this is completely, it's not related to complex numbers at all. Because you see there is no I inside it, and we actually solved this problem, I told you, in Math 5 in the topic of mathematical induction. So it's not related to the complex numbers. And there are solutions that you don't need complex numbers. But I want you to show you a solution which you can use complex numbers to answer this. So, and that is the main reason that why people got interested in complex numbers, because you were able to solve something in the real analysis using the techniques and tricks and concepts in complex numbers. So this is the first reason that why people got interested in complex analysis. So do you remember, just Carl Friedrich Gauss started with just a mathematical curiosity. Let us assume that there is a number whose second power is -1. Yes, this might be ridiculous, but is this problem ridiculous? No, this problem is not ridiculous. I can also give you probably a physics problem that is related to finding this series. So this is not a ridiculous problem, but then you see that complex numbers, that mathematical curiosity gives you another method, a completely different method to solve this problem. Yes. So this is why complex numbers are actually really important. There are many, there are integrals that you cannot solve them using real numbers, but you can map that integral to a complex plane, because the techniques and tricks in complex analysis are more broad. And one of the reasons is that when I have equality between two real numbers, that is one piece of information. But when I have equality between two complex numbers, that's two pieces of information. The equality of real parts, the equality of imaginary parts. So somehow the equality of complex numbers gives me more information, yes? So, let me try to solve this one. I don't want you to be so creative to find everything from scratch, but try to follow what I'm writing here for you. Okay? So, what I'm trying to say is that instead of calculating this series, let me calculate this series for you. So, let us consider this sigma e to the power of I k theta. This theta is that theta, but k is a number from 0 to n. Let us forget about this series. Let us calculate this series. So is that understandable? What is this series? If I put k equal to 0, it becomes e to power 0, 1. If I put 1, it becomes e to power I theta. If I put 2, it becomes e to power 2I theta. And then if I put 3, 3I theta, and it continues until the very last step. Yes? So momentarily forget about this question mark, try to focus here, and then try to find a closed formula for this sum. A closed formula, give me a formula which does not contain these dots, but it is equal to this one. This is extremely simple. This is probably hard. Why this is extremely simple? So might be I'm exaggerating. By extremely simple, it is easily doable. Extremely easy to come to mind what to do. That was what I meant. It's extremely easy to know what to do, but of course it takes time to do it. What that is? It's famous.
It's that formula.
No, it needs that, but not now. What type of series is this? We studied it in Math 5, if you remember. You also studied it in Math 1C. Not the type of this series. What type of series is that? This is a sum. You had two sums. Arithmetic sum, geometric sum. So that's a geometric sum. Yes? Why is it a geometric sum? Every time it is being multiplied by a fixed number. What that fixed number is? 1 has turned into this one. This has turned into this. This has turned into this. So I am multiplying every time by... Come on, it is easy. e to the power of I theta, yes? So do you agree? If I multiply this by e to the power I theta, this becomes this. If I multiply this by e to the power I theta, it becomes I theta plus I theta. If I multiply this by e to the power I theta, this becomes this, yes? So every time I am multiplying the previous term by a constant term. And that constant term, do you remember what was the name? It was the common ratio, yes? So the common ratio here is e to the power I theta. The first term is 1. How many terms are there? How many terms are there? Yes?
N plus 1.
N plus 1. Because from 1, 2, 3 up to n is n, and one more it's n plus 1. So the number of terms is n plus 1. Now you can say that I have forgotten the formula, so I will give you the formula. But recognizing that this is a geometric series is on you. So you need to realize that's a geometric sum, and then you can go and look up the formula sheet to see what is the sum. So the sum for n terms is equal to the first term times 1 minus e to the power of the common ratio to the power of n divided by 1 minus r. So this you can find in the formula sheet. For the sum of the first n terms of a geometric sum whose first term is a and its common ratio is r. So, but understanding that this is a geometric sum, you should train your eyes for these things. Okay, you might forget the details of the formula. It's not a problem. You can look it up, but no one will tell you that you need to understand. You need to understand that this is a geometric series yourself. Okay, let us now, instead of n, I have n plus 1 terms. So let me just write n plus 1 instead of n. Yes. So what can I do? It becomes this question mark. So let me call it s. S is equal to, the first term is 1, so forget about it, and then 1 minus e to the power of I theta, which is playing the role of my r to the power of n plus 1, divided by 1 minus e to the power of I theta. Is that understandable? So I have just used the formula. Okay. So let me simplify this a little bit, so because we don't know what we are supposed to do. So it becomes e to the power of, I multiply these, so it becomes I n plus 1 theta. And then I have e to the power of I theta. Okay. I want to ask you something, but you might say that why it is useful. Forget about that part. If I want to find the real part of capital S and the imaginary part of capital S, at this moment, you might say why this is useful. Be patient, you will see why it becomes useful. Now I'm asking you, how can I find the real part of S? How can I find the imaginary part of S? Yes?
Just wondering, can we assume that the formula works even when we're working in complex numbers?
Yes, because in these formulas, because the reason is that if you go and see the proof of this formula, in the proof of this formula, you write your series and then you multiply them by a number and add them together. All those rules are still valid. Yes, because we proved that in the previous session that if I have e to power z, e to power w, it becomes e to power z plus w. Because this formula is also valid for complex numbers, so what you have written, what you say is right. It actually works. Is that understandable? So go and see the proof of this. The procedure that gives rise to this formula is also valid based on these formulas and complex numbers. Yes, that's possible. Because, for example, I am using one formula here. I'm saying that I'm multiplying these two. But that's essentially the same thing, because e to the power of z to the power of 2 means e to the power of z times e to the power z. But before we showed that this becomes e to the power z plus z, but z plus z is e to the power 2z. This is like that I am multiplying these two. So that rule that I am using there is valid, even for complex numbers. Yes. But this is not a hard question. Might be this is a level 3 question in Math 4. If I ask you what is the real part of S and what is the imaginary part of S, this is not something hard. At least the starting point shouldn't be hard. How do you find the real part and the imaginary part of S? if you want to find an imaginary part and real part of a complex number, you need to write it in a standard form. There is nothing else we can do. This is not a standard form, it's far away from being a standard, but what I want to do, I want to write it in a standard form. Okay? So it means that if I want to make it in a standard form, I am dividing a complex number by a complex number. There is only one rule for that. So this is the way that you need to learn. If you learn it in this way, this is instantly coming to your mind. I want to make it a standard, so this is a division of two complex numbers. Do you remember what was the trick for division? Yes? Multiplying by the conjugate. So that should work. Might be it is harder, but that is the only way. Yes? So what I do, I would write 1 minus e to the power of in plus 1 theta, and then divided by the same expression. But I multiply, this is what I want you to ask. I want to multiply the conjugate of this one. Can you tell me what is the conjugate of this? You see, we had a lot of formulas. So do you remember what is the conjugate of this? What is the conjugate of this? It's the conjugate of the first one minus the conjugate of the second one, yes? Okay, what is the conjugate of this one? This we learned last session, I think. If you remember, we learned that the conjugate of e to power z is e to the power of conjugate of z. We also learned that. So I can, and what is, so it means that this becomes the conjugate of 1 minus the conjugate of this. But what is conjugate of 1? It's 1 itself, because the imaginary part is 0. Do you remember what's conjugate, yes? When I say a plus bi conjugate, I mean keep a as it is, change the sign. This is the meaning, yes? Now can you tell me what is the conjugate of this? Yes?
E to the power of negative I.
Negative I theta, because this conjugate will go here and it changes sign. So this becomes e to the power of negative I theta. Exactly. So what I mean, so I have to multiply this. Yes? So this I have to multiply. So this is a little bit strange because you have used to this put positive, but positive doesn't work. The point is to make it conjugate. The conjugate in this simple case becomes negative, or if it is negative, it becomes positive. But the conjugate of this, you see, I have calculated the conjugate and I got this expression. Yes? So I have to multiply by this and then divide by the same thing. Okay, now let us see how it goes. I have to multiply, be patient and to multiply them. So 1 times 1, 1 times that expression, this times that, and then this times that. And then in the denominator, 1 times 1, 1 times this one times that, and this one times that. Yes? Okay, we have to do a lot of simplifications now. So let us start from the denominator. Yes? So what is the answer to this part? What is the answer? Are you confused or not? Yes or no? Are you following? Yes, Malhab?
Little bit.
Confused? Which
I'm
part?
not confused, I'm following.
Okay, okay.
But it's, I'm tired.
I understand. Okay, okay. But what is this one now? This shouldn't be hard, yes?
1.
It's 1, yes? Because e to the power of I theta, I need to add them, it becomes 0. So e to the power 0 is 1, but with this one, with that one becomes 2. Yes? But what can I do here? Let me clean, we don't need them. So what is that one now in the middle? So let me calculate this one. So minus e to power minus I theta minus e to power I theta. First of all, I can factor a minus out. It becomes e to power minus I theta plus e to the power of I theta. Yes? But do you remember today we just talked about sine z? Do you remember what's no cosine z? So what was cosine z? Do you remember? It was e to the power of iz plus e to the power of minus iz divided by 2. This is valid for all z, so let me change z to theta. Because that is valid for all complex numbers, including real numbers, because real numbers are also complex numbers. So then it becomes e to power I theta plus e to power minus I theta divided by 2. Yes? So e to the power of I theta plus e to power minus I theta, which appears here, is 2 times cosine theta. It's nothing except that. There's a negative sign here as well. So this becomes negative 2 cosine theta. And in the numerator, let us see what happens. What can I do? I can write 1 minus e to power minus I theta. Yes? I cannot do anything here, so let me just write it down. Yes? And then what can I write here? I am multiplying them, so I should write e. The exponent here is I n theta. I'm multiplying them, and then I theta. And then I have e to power minus I theta. Yes? I just expanded this and wrote it here, and then I am multiplying. If I multiply them, they will be added, they are cancelled, so this one is left. Yes? So that is actually, that is the formula, so we need to continue a lot, of course. Yes, but what I have to do, I need to simplify things a lot actually. So how can I do that? Okay. So let me write something for you. First of all, I factor a 2 out here. And then what can I do? What can I write instead of this? I can write 1 minus. So I told you that e to the power of I theta is cosine theta plus I sine theta. If I ask you what is e to the power of minus I theta, I need to change theta to minus theta, but cosine of minus theta is the same. Sine of minus theta is minus sine theta, yes? These are the formulas. So I need to plug them in. So this one is this one, but there is a negative sign behind that. So this becomes negative, this becomes positive. Yes? And then when I go here, the same story, but instead of theta, I have this combination. So this becomes minus cosine n plus 1 theta plus sine n plus 1 theta. Of course, there is an I here as well. So I am using these formulas here, here, and here. Yes? For the last one, I will write plus cosine n theta plus I sine n theta. Do you agree? So that is actually this one. But my goal was to write it in a standard form. In a standard form, it means that I need to have one real part and one imaginary part. Okay? So this one, this one, this one, and that one doesn't include any i's. So that is the real part. So let me add them. 1 minus cosine theta plus cosine n theta minus cosine n plus 1 theta divided by 2 1 minus cosine theta plus, let me factor an I out. This one has I, this one also has an I, the last one also has an I, yes? So this becomes sine theta plus sine n plus 1 theta plus sine n theta, yes? Divided by the same expression. Yes, is that understandable? So that is, you can consider it as an exercise, a hard exercise for writing this in a standard form. But what is the benefit of that? Let me concentrate only on the real part. Okay, now let me ask you this question. So let me clean these things, and let me write one thing that we need. If I ask you, what is the real part of S, can you answer that? No, it is clear. Yes, the real part of S is this big guy here. Yes. So, and then you see that this is exactly the same. So let me divide this by that. It becomes 1/2. Write it a little bit simpler. And then plus cosine n theta minus cosine n plus 1 theta divided by 1 minus cosine theta. So I hope that yeah, you can go and if you are interested to review the calculations, but we were able to get that the real part of S is this guy. Yes or no? Okay. But why do you think this is useful for calculating for answering the question mark? This I want you to now find a connection. Because all of these messy calculations are standard calculations. They are tedious but standard. I am not being creative in doing any one of them. I'm just following algorithmically the rules after the rule, you know? So, but now you need to be a little bit creative. You see, I wanted to answer this question in the set of real numbers. I actually designed a completely, apparently different question in calculating this series. And then I want to show there is a connection between this calculation that you see and finding the sum of this series. That is what I want you to discover. What is the relation? Yes?
Wouldn't the absolute value of the sum be equal to?
No, absolute value is not the problem. Yeah, the connection. Absolute value of what?
The sigma.
Absolute value of sigma means this.
Yeah.
But calculating absolute value of a sum, we don't have any formula for that. Yes, the absolute value of a sum, you cannot write the absolute value of the first one plus absolute value of the second. Unless you want to say how this become useful. Okay, if I ask you, how did I calculate the real part of S? You tell me that I used the geometric sum, find S, and what I did, then I did some standard tedious calculations, I got this real part of S. This is one way of calculating the real part of S. Is there any other way to calculate the real part of S? Because if the answer to this question is yes, the real part that I calculated in this way and the real part that you calculate in a different way should be the same thing. Is that understandable? So can you find another way, another completely different way? By the way, it's the most simplest possible way to find the real part of S. How do you find the real part of S? Remember that S is a sum, and you want to find the real part of a sum. It's extremely simple.
Take the real part of
Each one of them and add them. Yes, as simple as that. So this shouldn't be hard for you. The real part of a sum is the sum of the real parts. Because when you add the complex numbers, you add the real parts together and you add the imaginary parts together. That's true. So can you tell me now, so what is the real part of S in a different way? I need to find the real part of 1. What is that? It's just 1. Okay, can you tell me what is the real part of e to the power of I theta? E to the power of I theta is on the board. What is the real part? Cosine theta. So the next term is cosine theta. What is the real part of the next term? Do you agree? Because instead of theta, I have 2 theta. So this becomes cosine 2 theta, sine 2 theta. But the real part is cosine 2 theta. Now you see what's happening, yes? The real part of the next one is cosine 3 theta. And then finally, the cosine of the real part of the last one is cosine theta. So on the one hand, the real part is this. On the other hand, the real part is this. So they have to match. When we put them equal together, these dots are gone. So this is a closed formula for that. So this is how one way to discover the formula rather than having the formula and proving it using mathematical induction. So that is the weakness of mathematical induction, because you need to have a formula in its entirety and then you can show that that guess is a correct guess. But guessing in that case is not that easy, by the way. Do you agree? For example, if I put n equal to 1 and then I put 2, can I guess that the pattern is this? It's not that easy. So you see that here, it's hard problem, I agree. It's a hard problem, but I wouldn't say that's hard. But hard means that you don't know where to start. This connection was hard to discover if you are not experienced. But if I ask you to find the real part of S for me, this is tedious but standard. Yes, I am following standard calculations. I want you to differentiate between hard and tedious in mathematics. Hard means that might be the answer. Combinatorics is hard. Yes, because I can cook up questions that the answers are just, I don't know, 3 times 2 factorial times combination of something. It's just one, I don't know, half a centimeter. But coming to that is very hard sometimes. But these are standard calculations, even though they were tedious. If I want you to be able to improve your skills in calculations. So now we have our formula, you see? So we have our formula here. Do you think if I take this away and I change cosine to sine, can you answer that one right now? Or not right now, everything is not on the board. But do you think I can ask you the same question for sine instead of cosine? Just using the same method. But this time, what should I calculate instead of real part?
Imaginary.
I should have to instead calculate imaginary part, yes? And the reason that why 1 doesn't appear, because when I put, what happens? Yes, because when I put 0, sine of 0 is 0. This is why you don't see 1 there, yes? But it is clear, I can ask you the same question, but instead of cosine, put sine, and then you calculate everything up to this point, but you take the imaginary part, and compare it with the imaginary part. They again should match. So it means that not only you were able to find this sum for cosine, you can also find a similar sum for sine. Is that understandable? Okay. So, yeah. There are many things that we can talk in complex numbers and in mathematics, but I think that's a fair point to stop. At least you have been exposed to a little bit harder problems and find a connection between real numbers and imaginary numbers. Okay. Do you have any questions? I think this is the last session of all the sessions this year, yes? Okay, so if you don't have any questions, I can stop this video from being recorded.